Greetings everyone, I'm Triet, a researcher from CREST at the University of Adelaide. I would like to present our paper, DeepCVA, Automated Commit Level Vulnerability Assessment with Deep Multitask Learning, accepted in ACE 2021. This work is authored by me, David Hin, Roland, Croft, and Professor Ali Babar from the University of Adelaide, and partially funded by the Cybersecurity CRC. In this study, we propose a novel deep learning model to assess the detected vulnerabilities in code commits to enable developers to prioritize and address vulnerabilities earlier compared to existing techniques. As part of software development, developers frequently need to scan their code to detect and resolve as many bugs as possible. Among the bugs, security-related ones, or so-called vulnerabilities, usually require special attention as they can make a system prone to cyber attacks, leading to catastrophic consequences. Ideally, when a new vulnerability is detected, developers will try their best to fix it as soon as practical. However, it's no longer that easy when too many vulnerabilities are found nearly at the same time, especially for large-scale code bases. We know developers are busy with many different tasks, thus they would not have enough time and resources to address all of these vulnerabilities at once. Now a burning question arises: which vulnerabilities should developers prioritize to fix, as not all vulnerabilities are equally dangerous, and how to perform such prioritization? Currently, to prioritize vulnerabilities, researchers and practitioners are using a well-known framework called Common Vulnerability Scoring System, or CVSS in short. Essentially, CVSS provides various metrics to quantify the exploitability, impact, and overall severity of vulnerabilities. In practice, all of these metrics are useful to perform thorough vulnerability assessment to prioritize the fixing. However, the assignment of CVSS metrics to ever-increasing vulnerabilities is time-consuming and requires significant expertise. Thus, over the last decade, there's been a rise in the literature to automate this process. Specifically, thanks to the emergence of large-scale vulnerability data in the wild, many studies have proposed data-driven methods, leveraging machine learning, deep learning, and natural language processing to predict these metrics. Currently, most of the studies have focused on using the vulnerability description or reports in large vulnerability databases like NVD, National Vulnerability Database, to determine a single CVSS metric at a time. However, our analysis found that these vulnerability reports required for current assessment techniques are not published close to when these vulnerabilities are first added to a project as part of code commits. Actually, the time gap is more than 1,000 days or 3 years on average, potentially leaving software projects open to cyber attacks for a very long time. Here, another important question arises: how we can bridge this time gap and perform vulnerability assessment earlier or just in time when these vulnerabilities are first injected into a code base. To address this gap in the literature, our work first proposes to shift vulnerability assessment from report level to commit level, where vulnerabilities are first added to a software project, which in turn supports earlier prioritization of vulnerabilities. Moreover, we observe that CVSS metrics can be related. For example, an extremely severe vulnerability likely has high exploitability in impact values and vice versa. Thus, we investigate the possibility of predicting all CVSS metrics simultaneously in a single model to reduce the model training and maintenance time compared to having separate models for individual metrics. To fulfill these two aims, we present DeepCVA, a novel deep learning model to automate commit-level vulnerability assessment with multitask learning. Here are the three main components of DeepCVA. Firstly, to enable assessment right after vulnerable code is added, DeepCVA accepts input from vulnerability contributing commits or commits that contain vulnerable changes. A VCC, like any other commits, contains hunks with both deleted and added lines, as well as unchanged lines. As recommended in the literature, we treat deleted lines and added lines separately. We also incorporate the respective context of the changed lines. Here we adopt the closest enclosing scope, like if, else, for, while, do as context, and it gives a decent trade-off between size and relevance of context. Specifically, previous studies found that vulnerability fixes are usually local and affect nearby code, so we don't always need to use the entire function or class, reducing the relevant code context. This type of scope is also more flexible than a predefined context size, and the exact context size likely varies for different hunks. After extracting hunks and context, we have 4 inputs to extract features from using a shared feature extractor, which significantly reduces the model complexity and time. This shared feature extractor consists of a 3-way convolutional neural network connected to a gated recurrent unit augmented with attention mechanism to avoid the information bottleneck issue. These components extract different n-grams and their sequential order from each input. To support prediction of all CVSS metrics simultaneously, the commit vector concatenated from the output of the shared feature extractor is fed into a fully connected layer for each CVSS metric. This task-specific layer helps customize the shared features for each task. Finally, the task-specific features enter a softmax layer to obtain task-wide predicted labels. The weights in the model are trained end-to-end using atom optimization and backpropagation algorithms. To evaluate the performance of DeepCVA for commit-level vulnerability assessment, we set out to answer the following 3 research questions. First, we compare the performance of DeepCVA with those of various supervised and unsupervised learning models to examine the usefulness of the proposed DeepCVA for commit-level vulnerability assessment. Secondly, as we can see from the previous slide, DeepCVA has multiple components. So research question 2 quantifies the contributions of such components to the overall performance of DeepCVA reported in research question 1. Furthermore, because some of the CVSS metrics have quite few entries, research question 3 investigates whether class rebalancing, a commonly used technique in imbalanced data scenarios, will improve the performance for these cases. To answer these 3 research questions, we use the following methods for data collection and model evaluation. For data collection, we follow a common practice that uses the SZZ algorithm to trace VCCs from the respective vulnerability fixing commits, or VFCs. The 3 sources of VFCs were NVD, GitHub Security Advisories, and VolusDB. We obtained more than 1,200 VCCs and their corresponding CVSS metrics for our dataset. After that, we apply a 10-round time-based validation technique on such dataset to maintain the temporal property of vulnerabilities for evaluating the models as recommended in the literature. In each round, say round I, we use all the folds from 1 to I for training, fold I+1 for validation and tuning hyperparameters, and finally fold I+2 for testing. We then repeated the same process 10 times. We use Matthews Correlation Coefficient MCC as the main evaluation measure as it considers all the cells in a confusion matrix. We also reported macro F1 score as is commonly used for multi-class classification tasks. For deep learning models, we average the results over 10 runs to reduce the randomness. We also tune hyperparameters to obtain the optimal performance of the models. Now I'll present our key findings. In research question 1, we compared DeepCVA against various baselines that were either used for report level vulnerability assessment or other commit level tasks. Specifically, we considered a combination of 3 feature extraction methods, 6 machine learning classifiers, and 3 types of model output. We used k-means clustering for unsupervised learning. For all output fully supervised learning models, we concatenated all CVSS metrics of vulnerability as a single string for prediction. Here we mainly report result for MCC as is the main evaluation measure. The F1 score results can be found in the paper. DeepCVA on average significantly outperforms the best baseline by 38%. And if we only take the best DeepCVA run in each round, the improvement would increase up to 60%. Overall, all output or multitask prediction is better than single task and unsupervised counterparts. In research question 2, we evaluate the performance of DeepCVA's components. For each component, we first remove it from the model and then combine the parts before and after it to create a new model. Overall, all components have a positive impact on DeepCVA's performance. Notably, using own components in shared feature extractor is better than using them individually. Attention mechanism is particularly important, probably because code input is usually long and the information, especially of the initial code tokens, can be lost after passing through multiple time steps in the GRUs. Commit context also adds great value to commit level vulnerability assessment compared to using only the changed lines. And again, multitask learning doesn't only improve the performance as in research question 1, but it also increases the efficiency more than 6 times compared to single task models. As mentioned before, many CVSS classes are severely imbalanced, and most of them even constitute less than 10% of the dataset. To handle such imbalance, we investigated 2 commonly used techniques, random oversampling ROS and SMOTE. ROS randomly duplicates entry in the minority class, while SMOTE generates random synthetic samples between entries in the minority class and their nearest neighbors, which will tune the number of nearest neighbors for SMOTE. However, we want to emphasize that these class rebalancing techniques cannot work with DeepCVA, as DeepCVA's features are trained end-to-end. Therefore, research question 3 also checks whether DeepCVA is still better than the rebalanced versions of baselines. Here's the performance without class rebalancing. And here's the performance after applying the class rebalancing to the baselines. Overall, Roland and SMOTE improved performance for most of the cases except for XCVA. However, DeepCVA still maintains the best performance without using class rebalancing techniques. We believe that there's still room for future research to explore techniques to handle imbalanced class for multi-class learning. Here are the key takeaways of our study. We're the first to tackle just-in-time vulnerability assessment and propose a novel deep learning model, namely DeepCVA, to make the first progress for this task. Through extensive experiments, we found that DeepCVA outperforms many baselines even without using class rebalancing techniques. Multitask learning also proves to be much more efficient than single-task models. Last but not least, DeepCVA moves one step closer towards our vision of having a unified and reusable solution for tackling relevant tasks to address vulnerabilities early. If you're interested in our work, please scan this QR code to read the preprint and visit the GitHub link for data and code. This also concludes my presentation. Thank you very much for your listening. If you have any questions, I will be happy to answer them.